what is a field? Okay.
Oh boy, here we go.
And we left off the other day with our science critic. Can you believe a fellow who criticizes the scientific method? Unbelievable this day and age, yes.
Well, you criticize the scientific method.
No, I defend it. In fact.
Really?
Yeah, the real scientific.
Oh, the real one.
Okay, so this is what he said. He said, there are some things like field, there are things like fields. So he thinks a field is a thing. Seems completely foreign to us, but when you learn about these things, right, it makes it easier to understand what is happening. Yeah, the problem is that a field is not a thing, okay? And so that's the first problem. We also showed James Maxwell. He wrote this mid-19th century. Field, the space in the neighborhood of the electric and magnetic bodies. In that space, there is matter in motion. Okay, so and there you see it on the right. You see, in this case, a magnetic field. And you can see as soon as you put the magnet inside that tube, all the iron filings underneath the water gradually, one by one, is being picked up and put closer to the magnet. That means there's something in motion.
Not necessarily.
In magnet. Okay, explain it otherwise.
Gravity would also be.
Well, this is against gravity, essentially. Yeah.
Gravity would, by that definition, also be matter in motion. If you're pouring out a bottle of water, gravity keeps pulling it out.
Yeah,
but it's not in motion.
Okay, but this is gravity downwards.
Even then, gravity's not really in motion.
Gravity is not in motion, correct? Well, it is in a way. Hold it. It is in a way, because what you have is the more and more ropes as the distance between two objects decreases. So in that sense, there is motion of the ropes, not pulling, but you have more of them. So where did all the ropes in the next frame of the universal movie come from?
The rope angle motion. That's an abstract version
in that sense, there is motion at least under the rope model, right? Yeah, well, even under the mass model, because what is mass?
Bullets.
Well, yeah, but I mean, the way they look at gravity is that mass pulls on mass. Yeah. How it does so, we don't know, but the distance decreases. Again, gravity is a dynamic thing in that sense.
I think we've all had the observation of the two things touching each other, but how it does that, the distance decreases. We got that far. Okay, how, buddy?
Okay, and so just want to mention that a field is something in motion, and you have to separate the something from the in motion. Okay, and here's an example. Okay, here's a cascade. Cascade in ordinary speech is a noun. It is not a noun for the purposes of physics. A cascade is not a thing. Water is the thing. Cascade is what water does. Okay, so we have to separate the thing, which is water, from cascade, which is what water does.
Well, I guess it's a nounification of a verb.
Yeah, but see, we have to be careful with that in physics, because we cannot use something which is a verb like orbit or motion.
Moving the cascade gets very
and turn the word motion into a noun, not in physics. That's okay in ordinary speech, but not in physics.
It's like water spiral. Let's not move the water spiral. Let's just move the water.
and you have to learn the language of physics. The language of physics is different than ordinary speech. You cannot continue, or you cannot bring words indiscriminately from ordinary speech into physics and say, well, it's a noun in ordinary speech, so I'm going to use it as a noun here. No, only objects can serve as nouns in ordinary speech, in physics. You don't say, like I always give the example, the orbit of Jupiter. That's not the way you say it in physics. You say Jupiter orbits. Jupiter's the noun, orbits what it does. You don't talk about the orbit of Jupiter in physics, at least treating it almost in that case as a noun.
You could, but like with a lot of care.
But you see a lot of this because like the word orbit, that's where the word orbital came from for the electron orbital. They turned this orbit into a thing, like a channel in which the electron rolls around.
But the reason that they talk about that is because when they talk about an orbit moving, you can kind of understand what they're talking about. It used to go around here, now it goes around here. But in physics, the better way of saying that would be it was orbiting around here, and now it's orbiting around here. Instead of saying the orbit moved. Yeah, and that's how a lot of these verbs become nouns. Orbit became orbital, and field, which was what matter in motion, became a thing. And so on. And the same thing happens with mass. Energy as well. People think mass and they say, well, yeah, it's a mass that's moving. The ball is moving. They say the mass is moving. No, the ball is moving. Mass is what it weighs. It's a property of the object. You can't say the property moved. Yeah, it's like saying the red moved.
And energy is and energy is the same thing, or the size.
But it's hard to really wrap your head around that.
It's
as an outsider.
You got to understand the language.
And it's not really new language. It's just we're bringing it back to what do we really mean? Because it's not new language.
What it should have been.
Yeah,
what it should have been from the start.
The thing is, people get away with murder with these moving reds and stuff.
Okay, so here's one fella, and he wonders about this word field. Okay, he says you can understand everything as long as you introduce spirits. In other words, I said that saying, yeah, if you're going to introduce spirits into your theory, then you can explain anything, and the other person, I don't know what the other person can understand, but you can explain anything. And so he says, how did I equate field with spirit? That was his concern. And I'm saying, yes, look, every time you use the word field, you could just as well have said spirit, because you're going to use it as like a joker in a rummy game. You're going to put it in there every single time that you need it. You just say, oh, the field did it. And you fix the problem. It's like, oh, okay, now I understand.
Yeah, I don't understand.
No, you didn't understand squat, because all you did was introduce a spirit, and the spirit did it. And oh, okay, I understand now. It's more or less like that. But I'm going to address his second comment as well. He said the following: he said, where does it say that you learn about what is meant by a field means that now you understand everything and we're done? What else is there to learn? Or in short, where does it ever say in science that we're done and that we've learned all there is to learn?
Well, more like we've learned all that we wanted to learn for the moment. Isn't that a more accurate?
Well,
if someone has a question,
I'm going to address
with
that.
a field.
I'll overrule you. Okay, that's the way I see it. Here's let's say you have an equation, right? And you have some invisible, intangible entity out there, right? You don't know what it is. All you can do is see the visible stuff, touch the tangible stuff, but not the intangible, invisible stuff, okay? So in the case of gravity, we don't see the invisible, intangible stuff, okay? So we say it's the spirit. That's how they used to say it in the old days, traditional religions. Today we say it more scientifically. We say it's energy. Or it's the field,
It's not Zeus anymore. Yeah, Zeus changed his name to energy.
It's the god of mass, the god of energy now, or any of those. And so, or the field, yeah. And so the question is, what if the mathematicians are applying their mathematics to the wrong, the wrong, I guess that would be the best way of putting it, the wrong invisible, intangible mediator that Mother Nature uses. And here's an example, okay? Here we have ants, okay? Those are the particles. And at the bottom, you have a little wave there. That's the snake. Well, obviously, if you think that between two objects, what's happening is a bunch of ants are going from A to B, that's a little different if you guessed something else. You guessed that maybe it was a snake that lay between two objects and was just waving in situ, okay? So up and down in situ. If you're going to apply an equation, you do a study, and you're going to invent this equation and say, okay, I've got an equation for ants, and it turns out that Mother Nature is not using ants. Mother Nature is using a snake. Then your equations are worthless. And that's more or less the situation today in mathematical physics. What the mathematicians have done for the last 3,000 years is apply their equations to particles. Okay, so one thing is for them to use particles, another one is for them to hit it correctly and say, oh, it wasn't a bunch of particles that were flowing. It was something else, and it was actually a snake that was twirling in place, or people say a wave or whatever. A wave is different than a bunch of particles. In fact, you cannot reconcile particles with waves, not particles going straight versus particles going up and down and waving, for whatever reason, because they would have to be attached to each other in order to have this wavy motion. If some particles go up, what pulls them down? And vice versa. Why would the particles move up and down if they're all discrete particles? So you would have to attach them somehow. And again, if you're going to apply equations, you're going to invent equations, discover equations, or develop equations for ants, and it turns out that Mother Nature does everything with snakes, well, you just wasted, 400 years of research. That's what you did. Okay, your equations are worthless. Okay, so that's all I want to say. And the case with a field is like that. If, as Mr. Maxwell says, a field is matter in motion, we first have to discover what matter, exotic matter, right, in this case, invisible, intangible, only tangible to the iron filings, but certainly not to us, what entity could be moving in that area. Once you figure that out, once you have God's eyes and you can see, with your mind, what's in that region, what is that matter, exotic matter that's moving in there?
The equations are easy.
Not only the equations are easy, but you are at the end of the physics. You're at the end of science for the most part. Maybe there's some little thing out there that you haven't discovered, but for all practical purposes, it's the end of physics. It's the end of science. We have the explanations for how the universe works. So this fellow has this notion, which I'd like to destroy, that science is an ongoing process of discovery. That's not what science is. Science stops.
I like
Physics stops. Once we discover, for the most part, how this universe works, yeah, there are details.
You don't even have to say for the most part. You can take it all the way and say there's a certain way the universe works in chemistry, biology, physics. Pick one, and the answers are finite. The questions are finite. At
That's
some point,
true.
you
No,
know
this is
exactly how everything works. Maybe not you.
No,
But
no, this is my point. My point is that, people say, well, Bill, how do you explain this little thing here? And so, well, I don't know.
we'll get to that.
Yeah, I mean, it's like, I didn't even ponder it. I
Yeah,
never
yeah,
even
yeah.
knew about the event. So you cannot know of all the, little things that are out there in science, everything that
Well,
has
that's a
been
really
discovered.
good question. That brings up a really good question. The question is, how much, let's say, real physics have you not done because you've been busy trying to tear down the corrupt temple that science has become?
Oh, yeah, yeah, yeah. But
Like,
we
there's a
have,
lot of science you haven't done
yeah.
as far as this nitty gritty. You kind of stopped developing your own theories in a lot of ways.
Well, that's where I have some other fellows who do
Yeah,
that.
yeah, yeah. I mean, that's kind of why you're doing all these videos and
Yeah.
such, right? So
It's to get the main point
to get
out.
the main point out so
Yeah.
that people can work on the nitty gritty.
Exactly. Okay, so one fellow says, he continues with spirit. And of course, I replaced a couple of his words, right? He says, Lawrence is the force. I'll get it on the side.
Hey.
The Lorentz force is the force on a charged particle due to what? Electric and magnetic spirits. A charged particle is in an electric spirit will always feel a force due to this spirit. Yeah, we can replace the word
like
field with spirit because we have not understood anything by replacing that word spirit with the word field. So it wouldn't matter at all if you just put the word X, the letter X there, or the word spirit, or the word field. We understood just as much. We have no idea what a field is, especially if you're going to treat it as a thing when Mr. Maxwell says it's not a thing, it's something in motion inside a field. A bunch of somethings in motion make up a field. Just like a bunch of somethings in motion make up plasma. There is no physical object called plasma. Plasma is a process where something happens to the atom. Ionization. Okay, so you can't take a snapshot of plasma because when you do, you don't have plasma. Plasma is defined as something in
Well,
motion.
hold on. By that same logic, would that also apply to gases, solids, and liquids, where there's no such thing as a liquid because it's really just atoms in a certain state?
Well, what we say is that, in the case of plasma, it's the definition of the word plasma. What does plasma mean? On the other hand, the word table, there's no meaning to the word table. You point and say table because you named the object.
Yeah.
Okay, you're teaching the ET,
Well, but,
you're teaching him your language. In the case of plasma, we've got a different situation. It's a concept. It's defined as ionization. Ionization is a process. That's where the difference lies.
But the states are the same thing because they're essentially properties. There's no such thing as a solid. That's just the property that the atoms have when they're in a certain state.
Yeah, we're not talking about that because that line of reasoning is known as mereology. You're looking at what something is made out of and what it's doing. Time, what is it? There's a time slices, etc. We're not looking at that. We're saying, look, table is what I point to. That's an object. But plasma is not what I point to. Plasma is defined as something that is happening. So plasma is a verb, not a noun. Not for the purposes of physics. Okay, and here another fellow says a field is a geometrical blah 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 of an energy's interaction. So a field is an interaction. Well, if a field is an interaction, it's a verb. Okay, interaction is obviously an occurrence. It's a phenomenon. Okay, it's a verb, something in motion. And so a field is a interaction. Well, no problem. We know what it is now. It's a verb.
I mean, but everyone kind
So you can't say a verb moved.
Well, no, but everyone intuits that. Well, yeah, that's true. You can't say a verb moved, but everyone kind of knows that magnetism is a verb. There's something happening there. When you see getting them pulled, they're pulling. And yeah, it is weird for people to talk about a field doing the pulling because a field is usually a static concept as far as I understood it.
Yeah, people think it's a static concept, but you can see that when you put that magnet underwater, there's something going on there.
It's pulling.
The field is doing something to the iron filings. It's not like it goes bloop in one shot. It's like pulling one at a time. Okay, so it's important to understand that. Okay, so because of these notions of field as an interaction, we went to QFT, quantum field theory. Okay. See, originally in the 1920s, 26 thereabouts, they said, look, the world is discrete particles, and the particles ain't particles. Particles is a concept. It's not a thing. It's not a ball. It's not a little grain of sand. It's a concept. And that notion evolved, and today they've really gotten rid of it. If you tell a mathematician that a particle is like a discrete little ball, he'll say, no, you're absolutely wrong. You have no idea. You have no clue. Yeah. So what is it? Well, here it is. Okay, QFT was invented, and now they deal with field theory. What is field? Well, field means that there's this web of interconnection by concepts, I guess, because everything can affect something else at a distance. And they built this web known as a field. And then if you want to know what a particle is, the field vibrates locally, and that's what a field is, what a particle is. A particle is really a vibration, a local vibration of this extensive field that goes all the way to the edge of the universe, as the universe has an edge.
We're talking about the ether, or what?
More or less, it's the same concept.
Oh, I thought it was exactly the same.
You could say it's exactly.
But they don't use that word.
No, they hate that word, but it's like one of Nobel Prizes says, we deal with the ether every day, but we don't call it that because it's taboo.
Okay.
Okay, so here you see, what is quantum field theory? It treats particles as what? Excited states.
Excited state.
Yeah, there's going to be
State is already not a noun.
Well,
excited is a.
Well, it is. If you come to think of it, a state is. Wait till November. There's going to be a bunch of states that are going to be excited during the election. They're going to be all excited. Believe me.
An excited state, man. I feel like they just don't want to use objects.
No,
they're trying their hardest. It's not a particle. It's not a thing.
Because they call that philosophy.
They keep getting more and more away from physics.
Yeah.
Literally,
in fact, Max Born said physics has become more and more abstract. It turns out that abstract is the opposite of physics.
Yeah.
And so we're getting away from physics and more into abstraction.
When you just talked about the particle being not a ball, not a thing,
it's a vibration of a state.
It's less thing by the ear. Now you're saying even a particle is just an excitation.
Yeah, of excited states.
An excited state. That's
also called quanta. So there's going to be a lot of quanta this November when the states are excited. Anyways, other underlying quantum fields which are more fundamental than the particles. Again, the vibration of a field is what a particle is. The quantum field of a particle is what? A functional of fields associated with the particle. Great, we learned a lot.
They're getting so far away from physics.
Yeah, and what they talk about is interactions. As you can see, they talk about the interactions, and they represent them with Feynman diagrams. There you see one on the right. It's two electrons, and gamma there, that's light. Okay, that's the photon. You can see the squiggly line referenced down below. That's a photon. And okay, we understand photon. Electron moves, throws a photon at another electron, chases it away probably, or just the other photon picks up the light and recognizes the light. Great. No problem with light because it's a push force, electromagnetism. How about a pull force like the gluon? Okay, let's look at the gluon with one of these Feynman diagrams. Okay, here it is. Okay, this comes from a fellow who's wrote, says the Feynman diagram shows two up quarks exchanging what? A gluon. Okay, so we have the two quarks, okay, that's the green going to blue and blue going to green, okay, and in between there's a gluon that's sent, okay, or exchanged, you can say. Great, what's the problem with this? Well, the problem here is the following. Here we have that a gluon is what keeps the quarks from leaving the nucleus of the atom. And they always represent them with these bed springs. And you say, okay, I understand that. You know, the quarks cannot leave the proton or the neutron because they're held together by bed springs. It turns out that there are no bed springs in the standard model of quantum mechanics. So what the gluon is really a particle that's being thrown from one quark to the other, like you see here, where they say it's being exchanged. Okay, so it's being exchanged. And by throwing a gluon, not a bed spring, by throwing a gluon, how do you attract another quark? How does one quark attract another quark? That's the question they have to answer. And they don't answer, they avoid that question. They throw the gluon and they say it attracts. Great. What was the mechanism? What's the physics that underlies it? The ball
hit the ball and pulled the ball towards...
Exactly. That's exactly what a gluon is. It's a ball that pulls.
It's a baseball that pulls.
Yeah, can you imagine the pitcher throwing the ball and attracting the batter towards the mound?
Instead of hitting him in the head, he goes, zip! Pulls him forward. That'd be kind of cool to see, though.
So what is QFT, quantum field theory? Here it is. Quantum field theory is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. Okay, great. QFT is what? Used in particle physics to construct what? Physical models of subatomic particles.
Not very well, though.
Physical particles. I can understand a field when it's vibrating, like the one below. That field we can all understand, but, a field of numbers, And in condensed matter physics, to what? Construct models of quasi or quasi-particles. What are quasi-particles? Well, they're a collection of particles, okay, or a phenomena, really, okay? So they're what? Collective excitations.
What if someone said quarks are attracted by magnetism instead of gluons?
They can say anything because they can get away with murder.
But they but
they don't explain it, and they don't care about not explaining. Say, well, we don't understand it. If you don't understand, what's your theory? So we don't have a theory of physics. We don't have physical interpretations. What we have is mathematical descriptions, which is not the same as a physical explanation. And they dismiss that as philosophy. They say, well, that's opinion.
It seems like they just kind of give these like crappy. Even they know that it's BS.
But they
like,
know,
yeah, take it. Fine,
well,
for the peasants.
Not really. I would say it's half and half. You'll find a lot of them who actually believe that they have an explanation. They say, well, yeah, it sounds right to me. You throw the glue on, it attracts it, does it through negative momentum transfer or whatever nonsense they come up with. And to them, it's okay. Or like, who was it? Victor Stenger, professor who died a couple years ago, professor at Hawaii University. And he says, to a mathematical physicist, meaning a mathematician, particle coming back from time, it's not so weird for them. They accept that.
They changed their normal.
Yeah, it's like, it's okay. We can deal with that. Okay, so whatever. Okay, and so here we have what a particle is according to quantum mechanics. What was it? Is the excitation of a field, local excitation. Obviously, we're not talking about the entire universe, which is a field, vibrating. We're talking localized vibration.
But also a field. I don't know what they're talking about. They're talking about a fabric.
Well, here, you'll see it. We've got it illustrated, folks. You wanted to know what a field is, what a particle is, right?
Yeah.
Here, you'll see it illustrated for you. There it is. That is a particle.
Which one?
Yeah, that one.
Oh, all of it.
All of them.
That's a particle?
Yeah. Another one. Let me put over here. You don't like
a
the
lava
particle?
lamp. It's a lava lamp.
Yeah, what it is all those fields, little fields,
Blobs.
vibrating fields,
Blobs.
they make up a particle. So it's an excited field. The field is apparently it's excited.
But what's excited?
And all those things, whatever those things are, that's part of the field. So it's excited. So now you know what a particle is.
No, I don't.
Well, that was it.
Why
You don't get the challenge.
See, that's not excited. That's balloons inflating out of nothingness and then deflating into nothingness. That's what I saw. Not excitation.
Yeah,
excitation is too vague.
And that is even also true according to quantum mechanics, because they say particles pop in from the void. In other words, from the void they acquire length, width, and height. Suddenly, called virtual particles. Then immediately they go back to being whatever space was. Maybe a bunch of particles.
Void.
The void is a bunch of particles. They call it energy. That's hidden in there in the void. So we have this energy. The concept energy acquires length, width, and height, turns into a particle momentarily to make the virtual particle. Yeah. Then it goes back to being energy, whatever energy is, because that's what space is.
But that's what bothers me, that they create out of nothing. They're godding.
Yeah, they're godding.
They're we need a particle here. Boop.
Hey,
there you go.
If the Greeks got away with it, come on.
I get no. But that's really what I love most about your theories, because you just start off from the get go. Look, nothing can turn into something. Something can turn into nothing. The rest comes off of that. Really, even the rope itself and the thread and all that is really just offshoots off of that basic assumption. Nothing can turn into something. Something can turn into nothing. If you disagree with that, go to another school, because that's as basic as we're gonna get. If you think something can turn into nothing, or vice versa, then we're gonna agree to disagree.
Yeah,
because that's just a fundamental.
No, it's not agree to disagree. You put them in the net house.
Yeah, but that's what I mean. Get away from me, because there's nothing for us to talk about.
Don't touch that. And just in case, it doesn't stop with quantum. The field. Remember, general relativity is a field theory, and this is the field, space-time. If you ever wanted to see it, there it is. There's your field.
That's a nice wallpaper, though.
Yeah, but see, okay, now the canvas there, the hammock, the little lines, the little threads, that's space and time that you're staring at there. So the only question is, what is the gray or darkish stuff that forms backdrop to space and time? Because you cannot say, well, no, because that's space.
Oh, the void is. Oh, true. Yeah.
We cannot have space behind space.
The void makes things.
So we've already taken up space, because that's what the lines are. The lines are space and time, and so we don't know what the dark stuff that gives shape to the lines.
That's the void of the void.
Yeah, so that part we don't know. They never identify that stuff, and we're still looking for answers.
That seems like a basic thing that they never really even ask. The fact, anytime they show something, there's always something surrounding that thing. When you say, okay, this is space, space ends here. Okay, then what's around space? Or this is
because they do it all mathematically. Yeah. That's the issue. They don't conceptualize. They don't visualize it, because there's nothing to visualize in mathematical physics. What are you going to visualize? Mass, energy, force. You can't visualize time. There's nothing to visualize. Maybe a clock for time.
Really, they don't use their imaginations.
No, because they can't. Because they're dealing with mathematical concepts, which they call mathematical objects. Okay, and they say, well, can you visualize? I mean, I can visualize an object such as a table. Can you visualize a mathematical object such as force? And the guy says, no, I can't. But let me show you the equation or the numbers or whatever. No, I don't want to see it. I want to see what physical object. I want to see the cause, the mechanism.
Well, do you think a lot of the hate that you get from physicists comes from the fact that they work so hard to get the perfect equation, and you're just using your imagination. Like, what are we, kindergarten? Like, well, you think you could just come with your imagination and come up with the right answer?
Let me first correct you. They don't hate me. They absolutely love me.
But seriously, the fact that they're trying so hard to do all these equations with numbers, which takes a lot of mental energy, and you just come with imagination, like you think things can just be answered by imagination?
Well, let's answer that question. What did Einstein say? What did Feynman say? They both more or less said the same thing. One said, if you cannot explain it to a barmaid, you don't know it well enough. And the other guy said, if you cannot explain it to a 10-year-old, again, you don't know it well enough again, or something along those lines. In other words, physics is kindergarten stuff. An 8-year-old should be able to understand physics once we identify the invisible, intangible mediators that Mother Nature uses. As long as we're going to do it with particles, we're not going to be able to answer any questions because Mother Nature cannot use particles. We cannot explain a single phenomenon like gravity or magnetism with particles. So we should abandon the particle. The particle has been the killer in that sense. But if we replace that with interconnectivity throughout the universe, now we have a different universe. And now we can start explaining it in terms that anyone can understand, including an 8-year-old boy. But if you're going to go in there and explain with particles and then say, well, I cannot explain, but let me show you the math. The kid said, the 8-year-old says, I haven't even taken algebra, you know.
But it gets frustrating as the questioner because you'd never get your answer.
No, you don't.
You just never get an answer.
Go to Quora.
And then you get shamed for being too dumb to understand the so-called answer.
You got to take math at the
university. You're too dumb to understand it. Well, I'm asking the wrong guy then.
Okay, so what is a field officially? Okay, we got to find an official definition for field because these people say, well, it's an interaction, and we invented quantum field theory. It's a vibration of a field.
But you can't really say official because doesn't everyone just kind of give their own interpretation?
No, because there is an official definition of the word field for the purposes of physics. We need to put this up there so that people can compare these other notions that people have, interaction, and the fact that particle is the vibration of a field and it's just a number. What is a field officially? How is it defined? How is the word field defined? Okay, and here it is. Okay, we have field, a quantity. Okay, what is a field? A quantity.
We're all to the wrong start.
We could stop there with period, right? A quantity. That's what a field is. What is it? Represented by a number, another quantity that has a value, another number. All we have is numbers, values, quantities, amounts. Okay, for each point in space and time. What is a point? Well, a point it's misdefined as well. It's an exact location. That's what a point is, and it has no length, width, and height. No kidding. I mean, if it's a location, it's a concept, it had better not have length, width, or height, or you've drank too much beer. And then in space and time, well, what is space? Well, I like space. Space is the fundamental space. I love that one. That was a great definition out of the Wikipedia. And time, well, it's the continued blah, 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 past, present, and future. But past, present, and future is a synonym of time. You can't define past, present, or future without the word time. So all we have is a synonym. And what have we learned with all this? Absolutely nothing.
And if you're too dumb to understand it, well, that's your problem, right?
No. Then that means you haven't gone to college.
That's what I mean. Little Timmy says, well, I guess I'm never doing physics, and then he's out.
No, but if he does physics, meaning mathematical physics, and then he goes to college, then he gets brainwashed and says, hey, you dumb
They beat
kid.
You with the shame stick and you're not going to have a career stick until you just nod your head.
You got to fall in line.
Just, okay, fine. Yes, this is the way it is.
Okay, here are my conclusions. Okay, what is a field? It's defined as a bunch of numbers, but field is also widely treated as a thing. Field is also said to be an interaction, whatever that is, which means it's a verb. A particle is an excited field. Space-time is equivalent to a field, so we have no idea what a field is because it's all these things, all of the above. Okay, so yes, field is a spirit. Whenever you use the word field, all you said is the word spirit. You're doing traditional religion by saying, well, it's really scientific because we're using these scientific terms, okay? And quantum loves fields now, but they abandoned the particle. Now they like quantum field theory. That's the
It's more malleable. It's less. It's more vague.
It's more than that. It's more. You know what it is? It unifies the universe. It says that everything is really interconnected. This is the issue. And there you see it. It has abandoned the discrete particle hypothesis and now proposes that all particles are physically interconnected in a grand web known as field. Okay? So this is the issue. The issue is that now quantum mechanics has moved. It no longer is what it used to be in the 1920s. So maybe you were left behind or whatever. Quantum doesn't deal with particles anymore, with discrete particles, which is the way it started. That's what quantum really meant. They were dealing with the quantum, meaning a quantity, right? Localized quantity. They represented it with a ball, with a point.
A chunk of quantity.
But now they represent it with a point, but they qualify and they say, well, really, it's not a point. It's not a little ball. What it is the vibration and excited field. That's what it is. What's a field? Well, it's this thing that extends like a web all over the universe, but locally it vibrates, and that's what we mistake for a field. As soon as we put our probes there, it turns into a particle because we detect something and point-like, and we say, okay, that's a particle now. As soon as you take it out, because, according to quantum, the observer affects the universe, right? So we put the probes, we turn it into a particle, we remove the probes, it continues vibrating as a localized field. That's what a field is. I hope you understood it all.
Another thing that bothers me about all that is there are other, let's call them like branches of science, the way you would call it science. Like I'm talking about philosophers now, who quote physicists nowadays saying how the observer changes the experiment, and they're saying, you see how consciousness is actually a physical object that changes the universe, because as these guys are saying, when you look at something, it changes how it behaves. No, they're wrong too.
Yeah, this is the issue.
It's been scientifically proven that our attention changes the universe. No, it changes your subjective perception.
It goes on and on and on.
They stack BS on BS, basically.
Yeah.
And then you lose track of where the BS started.